All right, so let's take on this question then. Um, let's take on this question. It's a question that. Oh, before we do that, by the way, we're supposed to do B. We're supposed to do B. B is another question that you you it's something that you have to remember, right? And it's nothing hard. So in a sense, what is really happening here? Whenever we have carbon 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 14, radioactive carbon 14, that carbon 14 can actually produce nitrogen, right? When it goes through, because remember, if it's radioactive, right, radioactive substance tend to disintegrate, right, so that they can um, create more stable nuclei or nucleus or elements, basically. This radioactive carbon is basically going through a process of nuclear fusion, not fusion, of course, yeah. So what is essentially happening here? If we were supposed to write out that equation, that nuclear equation, then we would start off with obviously the radioactive substance. So carbon 14, right, which is radioactive, is going to create nitrogen. Symbol for nitrogen is N. Now the number of the mass number of nitrogen is 14. The proton number is 7. Now with any type of equation, chemical equation, it has to be balanced. So to really balance the equation now, it tells us that it loses a beta particle, which essentially is an electron. So this is how we go about doing that. So here's my beta particle. My beta particle does not have a mass. The mass is very small. But the charge of my beta particle now is -1 because it is an electron. 7 minus 1 or 1 minus 7 gives me 6. So at the end of the day, everything seems balanced. And then we can plus energy. We can plus energy over here, so because energy is going to be released in the process, right? So this is basically what the equation looks like. All right. Okay, great. Now we continue now to essentially find out the energy that is released in the solar fusion of therium or something of that nature, right? How we're going to treat this, we have to treat it as an equation, right? Now, further on in physics, if you do continue to do it, you're going to learn something, what we call the mass defect, right? Um, Further on, you're going to come to realize that energy and mass, they are equivalent. What it means is that the mass that uh, that the substance is going to gain, right, is going to be equivalent to the energy, so to speak. Because what's going to happen here, right, is that we are combining elements, right? In the process of combining elements, uh, that element is going to become heavier, right? And to measure the amount of energy that is released, right, we have to take into account the amount of mass that was added to the system, right? Which essentially is what we call the mass defect. But I'm not sure if the syllabus asks us to talk about the mass defect, but if it's in there, then you have to read up some information about it. So what we're going to do here, we're going to try to find the energy, because the energy is almost equivalent to mass. And after finding that mass, basically, we can now use Einstein energy formula to essentially uh, find out the amount of energy that was released. So the first thing I'll do here is to transpose to make energy become the subject. So energy is equal to H2, well, and by the way, H21 is an isotope of hydrogen, and I believe the word is deuterium, right? So whenever you combine two deuterium, right, you're gonna get helium. Well, my bad. Yeah, when you obviously combine two deuterium, you're going to get a helium element. What I'm doing here is to just transpose the equation. Right? So this would be the transpose equation. Now what you're going to realize is that there's going to be what we call a mass defect. You know, I mean, you would think that if I combine deuterium and deuterium together, that mass is going to equal to the mass of helium, but no, there's going to be an increase in the mass basically. So when we do this now, so the mass of deuterium is 2.0140 U. We'll soon talk about U, and we're adding that again to one more deuterium, 2.010. Well, my bad. So this is 140 U minus the mass of the helium, which is 4.0026 U. If you have any questions for me, please just remember to ask them. Let me know if you're understanding what's going on here for the most part. Taj, are you still there?
Yes, sir, I'm here.
Okay. So my energy is equal to all of this that we have just written right now. All I need to do is to just do the mathematics. When I add up 2.0140 U to itself, I'm going to get 4.028. I'm going to now subtract that by 4.0025 U. Now U is what we call the atomic or atomic mass unit, right? The reason for the whole atomic mass unit is because that the mass in kilograms rather is a very it's a large unit, and because we're dealing with very very small numbers in terms of masses, they use what we call the atomic mass unit, right? But there's a way how we can convert from atomic mass unit to kilograms, and this is what we are saying here, that U, which is what we call the atomic mass unit, right? So U is the atomic mass unit. So all of what you're seeing on the screen here, that energy is equal to mass basically. That's what we're saying, you know. So this difference in energy or this difference in mass is essentially equal to energy, right? So what it tells us is that if the mass is getting more, right, then it means that energy is being added to the system. So in the process of combining deuterium, right, energy is being added to the system, right, and we want to find out that amount of energy basically. So when I do subtract these values, I'm going to get, and by the way, you can't round up anything in these calculations. There's no rounding off that is allowed here. You have to use the exact values. So if we subtract these now, we get 0.0254 U, and this is equal to energy, right? Now, we're not finished. 0.0254 U, right, is the mass in terms of the energy. So we're basically measuring the energy in terms of mass, but we're not completely there as yet. So what I need to do now is to convert from atomic mass units to kilograms. So U, well, are not U, but energy is equal to 0.0254 times 1.66 times 10 to the minus 27 kilograms, right? And once I do that, this essentially is telling me the mass of energy, but it is not telling me the exact energy. So I have to now use Einstein equation that says the change in energy, right, is equal to the change in mass times c squared. So this energy that we just looked at a while ago is basically what we would call the mass defect, right? But the mass defect and the energy, they are closely linked together. So I'm going to take that mass defect now, and I'm going to times it by c squared, where c is the speed of light. So c is the speed of light, right? And c has a value of 3 times 10 to the 8 meters per second. Now, when I put in that value, when I work out the mass defect is 4.23 times 10 to the minus 19 times 3 times 10 to the 8 squared, which is equal to the mass defect. Then now, or the change in energy rather. So this now, when I do finish work this out, this is going to give me 3.79 times 10 to the minus 12 joules. So this is basically the energy. I hope it makes sense to you. I mean, it's a lot of working out and all of that. Probably just need a few more practice. What do you think about a question like this, though?
It's a lot of working out, sir.
Yeah, it's a lot of working out. Yes. Yeah, I know that. I want you to check.
I need a bit more practice.
Precisely. Mhm.
So could you go over another question like this, sir?
Yeah, the possibility. Let me check and tell you quickly. Um, I'm looking at one now in the textbook here, right? All right. Let me see if I can pull up that. I want to see if I can pull up a textbook on the computer. Just give me a second here.
I was thinking for the energy, that was just well, I'm saying no, that was wrong. But never mind. Never mind.
So what you want me to do now? I don't understand. What's gonna happen now? Hmm? So are you gonna still work it out or what?
Sure, can you work it out, please?
What do you remember from the previous question that we would have done related to this?
Well, it's you have the mass of uranium. Uh, sir, I don't really know.
No, do you remember when we said that the mass, right, is equal to, what do we say the mass is equal to?
Mass of what, sir? Uranium?
Not mass of uranium, but remember now, we're gonna use this equation. You remember the energy equation that we talked about? What is the energy equation that we talked about?
Atomic mass equals Z, which is the protons, divided plus the neutrons.
No. We're talking about energy, the energy equation, right? What was the energy equation that we used in the previous question that is related to this when we were trying to find the energy release? What is that? What is Einstein's energy equation? Happen to know? All right. Nevertheless, the energy equation is
E equals mc squared.
mc squared, exactly. Now we want to find mass. We want to find the mass, right? How did we find the mass in the last question? If you remembered.
We transpose.
All right. So what did we transpose now? Tell me.
Sir, to find out the mass, we added the protons and the neutrons.
No, man. This is a different thing, This is a different thing. Atomic mass is different, right? This is totally different. So simply put, this is how we're going to do this. So the mass that we're trying to find here in the energy equation is equal to the mass of the the elements before, or we could say mass before fission. Let's just say mass before fission. Subtract the mass after fission. Mass before fission minus the mass after fission. So what are the masses before fission? Look back at the equation. What would contribute to the masses, the mass before fission? Do you know?
Sir, did you say what would contribute to the masses before what, sir?
Before fission, before the fission of the experiment, because this is a nuclear fission experiment, right? So we want to know the mass before. So obviously the mass before would be the neutron and the 235 uranium, right? Those would contribute to the masses before. As it relates to the mass after now, everything else that comes after here, so xenon and this SR element, right? Plus these three neutrons would contribute to the mass after. Yes? Yes or no?
Oh, yes, sir. Yes, sir. The neutrons and the mass number.
All right, so we're going to work that out now. So the mass before, right, the fission experiment is going to be obviously, let me work that out separately because it's going to be a little bit, if we don't be careful, it can be confusing. So we're adding the mass before would incorporate one neutron plus one uranium, right? So once I go ahead now, I just need to add the masses. So I'm adding 0.00867 plus uranium, which is 235.04393, right? When I add up this is obviously the mass before. As it relates to the mass after, let me just add up this first and see what happens. So 1.00867 plus 235.04393, I get that the mass before is going to be 236.0526. And remember, we said you can't round off, no numbers here. There's no rounding off that can happen here. As it relates to the mass after is going to be, we have one xenon, right, plus one SR plus 3 neutrons. So we have to add up all of these masses. So xenon has a mass of 142.93489, right? Plus SR, which is 89.9073 plus 3 multiplied by 1.00867, and all of these, the units are obviously U, atomic mass unit, U. So let's just add up these numbers now, all right? Now I feel like this is possibly might be one of the questions that you might can see on the exam, who knows? So it's obviously important to understand every bit of these type of questions. When I do add up this, I get a total of 235.86793. And remember, the units are U, right? So if I do the subtraction now, I'm going to subtract 236.053 26U minus that number, I get that the mass is equal to 0.18467U. And remember now that we have to convert this mass into kilograms in order for us to use the energy equation. So we have to take the give me a second here. So we're taking the 0.18467, and we're going to multiply that now by what U represent. U is 1.66 times 10 to the minus 27. So 1.66 times 10 to the minus 27 kilograms. When I multiply that, I now get that the mass is 3.1 times 10 to the minus 23, well not 23, but 29 kilograms. We're not finished as yet. So to find the energy now, we're saying E is equal to mc squared. So I'm taking that 3.1 times 10 to the minus 29. I'm going to multiply that now by 3 times 10 to the 8 all squared. So let's do that. All right, so the answer I'm getting, E is going to equal to 2.76 for argument's sake times 10 to the minus 11 joules. All right, that's what we're getting so far. No, that's the energy. The question continues. It says that if the mass released in an alternative natural decay reaction is 9.98 times 10 to the minus 13 joules, which would be the preferred method for the production of a nuclear reaction station? It says justify your answer. So in a sense, they are just asking us to look at it and to compare the answers mainly. So if you check back the question here is talking about a nuclear scientist, right, who is doing an experiment to create some type of energy using some artificial radioactive decay process, right? Now, they're now asking us to compare to see which one of these would be the preferred method, right, for the production of a nuclear power plant. Now, which one of these methods you might think about, you might agree with here? Which method do you think you would use?
Sir.
Yeah, go ahead.
Sir, the method you just used?
Not necessarily. I mean, remember we're comparing things now. So this procedure is a natural decay reaction. The other one is an artificial decay process, right? Now, I believe based on what they want us to talk about, we just need to compare the energy values, right? So by comparing the energy values here, so when you check it out, um, this energy is much more than this number. This energy that we calculated from the artificial process, right, is 2.769 10 to the minus 11. Now, when you compare that to the natural decay process, the natural decay process is going to give us less energy, right? So I believe the artificial method would be more suitable because you're getting more energy from it, right?
Sir, repeat that please from the start.
Okay. So the energy that we calculated just now, right? That energy is the energy that would have been released uh, in the artificial process of reacting uranium, right? Now, the question here is saying that an alternative method was used, which is a more natural process. When we look at the energy that is released, that energy is much smaller when compared to that of the artificial experiment. So the best thing here is to say that I would prefer the artificial method because of the fact that I would get more energy, right, when I use the artificial method when compared to the uh, the the natural method. To justify your answer, it says give the reason for your answer. I guess to justify the answer would you subtracting the values and realizing that there's more energy, right? That would be given off, right? When they say give the reason for your answer, I mean I don't like that part of the question to say give the reason because they would have already asked you to justify your choice, right? Already. So I don't know why they asked that question again. You know. But yeah, I think that's the answer that I would work with. You got me?
Sir, repeat please.
What do you want me to repeat? Am I breaking up a lot or what?
No, sir, you said you got me and I thought you said something before that, but no,
Okay.
I understand what you mean.
Okay, good. All right. So these questions, you definitely go have to practice some more of these questions, right? To ensure that you understand quite frankly. All right. Let me see now. All right. So here we have a question. Do you know what this question might be related to?
Refraction, sir.
Yeah. All right. So would it be possible for you to be able to can find out what would be the refractive index of the prism? Will you be able to can do that?
Find out the what, sir?
Refractive index. So look at that question and try attempt it for me. The first part of the question.
Sir, isn't the refractive index, the line that the angle of incidence is formed on?
No,
We don't really know if it's that, sir.
that is what we call the normal. So this line that you're talking about is called the normal. Now the refractive index just simply speaks to to what degree the medium is able to refract or to bend the light rays. Do you know what is the refractive index of air?
Of what, sir?
Air, air. Do you know the refractive index of air?
No, sir.
The refractive index of air is 1, right? That's the refractive index of air. It's 1. Always remember that. Now, the question wants us to find the angle of refraction, right? For when the violet light is at an angle of, let me repeat that. So they want us to find the refractive index, right, of the prism for violet basically. They gave us the angle of incidence, which is 30 degrees. So all we need to do now is to just remember the formula for Snell's law. Do you remember the equation for Snell's law?
The equation for what, sir?
Snell's law. Snell's law.
Sir, sine, sir, it's sine, the incident angle, how do I say this? Sine incident, it's n1 over n2 equals sine the incident angle over the refracted angle.
Okay, that's what you're saying. All right. Yeah. So technically speaking, that would be the equation. Yes. Right. Let me just confirm though. Right.
Sir, the sine of 20?
Yes, sine of 20.
Sir, it's 0.34.
All right. Give it at least yeah, 0.34. Yeah, indeed. And then now we'll just divide that by sine 30. That's going to be 0.5. So we have 0.34 divided by 0.5. So we're saying that N2, right, is going to have a refractive index of 0.6. 8. I mean, I'm trying to see now if this is, if so, right? I don't know. Let me just check something here. Because if we get the equation, if we don't have the equation correct, it can throw us off, you know. It can throw us off big time. So let's just look at right. So let's just look at that. Um, so it's the other way around, you know. I know that there's something there that, you know, would have kind of knocked us out of our feet. This is the equation, right? This is the equation. If we structure it the other way around, it's gonna throw us off. So that's why I know that there's something that went wrong with the question, right? So the easiest way to remember Snell's law, right? I'm going to show you. So we're going to work this back over because we should get a more refractive index, a higher value. The easiest way to remember Snell's law is by keeping the so if we're saying n1, if we say n1 sine theta 1 equal to n2 sine theta 2. If we keep the 2's together and the 1's together, we can't go wrong. Follow me? This is Snell's equation, by the way, just so you know that. If we transpose now, right, we could see that n1 divided by n2 is now equal to sine theta 2 divided by sine theta 1. Follow me? So this is the correct formula. So technically speaking, sine theta, I mean not sine, but n2 is equal to n1 times sine will be sine theta 1. Sorry about that. Let me just rewrite that again because you saw what I'm saying here though, Taj,
Yes, sir.
Yeah. Right. So once we do that now, we shouldn't go wrong in finding the answer. So what we'll be dividing, 0.5 by 0. What is it? What 0. What? Sine of 20. 0.34.
Sine of 20, sir?
Yeah.
Oh.
Right. So the refractive index is going to be 1.47. It doesn't have a unit. Now that we have this information, right, that's the refractive index of the glass, the prism. They want us to find the speed, right, of the violet light in the prism. Right, so there's another equation as well. There's another equation that we must remember. And that equation is clearly for when we're trying to find the speed. Do you know that equation?
Which equation, sir?
So they want us to find the speed of the violet light in the prism.
So the equation for speed.
Yeah, the speed of light in prism.
Sir, I don't know that equation.
Alright, so this is the equation. Sine of the incident, right, divided by sine of the refracted is equal to the speed in the incident, right, divided by the speed in the refracted. So all we just need to do is transpose to make V2 becomes the subject. When we do that, V2 is going to equal to V1 times sine theta 2 divided by sine theta 1. They gave us what V1 is already, right? They told us that the speed of light in air is 3 times 10 to the 8 meters per second. So all we just need to do now is to plug in the values. So we have 3 times 10 to the 8 times sine theta 2, which is sine of, well, we had worked that out already to be 0.34. Divide that now by 0.5. So let's see what the answer we're getting. So 3e to the 8 times 0.34. The numerator is a very large value. Divide that by 0.5. We get that V2 is going to be 2.04 times 10 to the 8 meters per second. Now what this is telling us, it tells us that the speed of the light would have decreased in the medium, which makes sense. Because the thicker the medium that you go through, you expect that the speed is going to decrease. All right.
Yes, sir.
All right. Now the question continues. It says to us that they want us to calculate the frequency of violet light if the wavelength in air is 430 nanometers. So just a while ago, we would have calculated the speed of light. Well, then again, they're talking about the speed of light in air. So we know the speed of, let me say that they're talking about the wavelength, right? In air, we know the speed of light in air, so they just want to find the frequency. So remember that equation that says V is equal to wavelength times frequency. We just transpose that to find frequency. So frequency would be equal to, speed divided by wavelength. Our speed is 3 times 10 to the 8. Divide that by the wavelength. That's going to end up giving us 43 times 10 to the 9. We have to put nanometer. We have to change the nanometers here. We have to put it in the equation, the -9, because if we don't do that, it's going to affect the answer. So that's why they would have showed you that 1 nanometer is equal to 10 to the -9. If you fail to make that conversion, if you forget about the nano, then it's going to affect the answer. So you have to incorporate that in it. So when we do this working out now, chances are we're going to expect that the frequency is going to equal to. So my frequency is going to equal to 6.9, right, times 10 to the 14. What's the unit for frequency? You remember the unit for frequency?
Sir, say that again.
What's the unit for frequency? Frequency.
Hertz.
Hertz, yeah. Yeah, man. Yeah. So basically, that would complete that question. You know what I mean? So